Hey y'all, I hope you're having a great day. Today we're going to talk about titrations. And the reason why we're talking about titrations is because yesterday we spent a lot of time talking about molarity and the concentration of solutions and how we can use those concentrations in chemical reactions. Well, today we're going to talk about titrations because basically titration is just a technique that we can use in the laboratory where we can react a solution of a known concentration with one of an unknown concentration in order to determine that the concentration of the unknown, right? And so basically we can do a reaction between two things, and when we do that reaction we can use it to help us determine the concentration of an unknown substance. And so it's what we were doing yesterday, but this is just what the technique is, and it's kind of funky, so I want to talk about it. Okay, so when we do a titration, again, remember, titration is just a technique. It shouldn't be scary. It's just a technique. We kind of have a setup that looks like this on the left side, right? So we have this great glass thing that we call a burette, right? And it's on a ring stand, and we use an Erlenmeyer flask. I think I forgot an E, but that's okay. All right, and so here's the thing. When we do a titration, first and foremost, when we have this stuff down here, first and foremost, we have to have something up here that we use. And a lot of time when we do titration, we do a titration between an acid and a base. So a lot of the examples that we're going to look at and the problems that you're going to work are dealing with acid and base, right? So they can be flip-flopped. It doesn't really matter, but one's going to be an acid, one's going to be a base. Now, if we look up here, and we have this reaction between our acid and a base, and anytime we have a reaction, it's going to be a double replacement reaction. So again, kind of the most common, if we take HCl and react that HCl with NaOH, we're going to get a double replacement reaction where we're going to form NaCl plus H2O, right? So we got these guys going together, and then the H and the OH going together to form the water. So that's kind of how that reaction works. And so what we would do when we do this titration is up here, let's say that we had our acid, and so here we would know what we're going to have. Let's say we had 0.1 molar HCl. And down here, we have our base, we have our NaOH, but the problem with our NaOH is we don't know its concentration. Now, in order for the titration to work, what we need to do is we need to know exactly how much of the base we put in there, right? And so we need to know what volume we put in there. And so based on this, let's just say we put in 200 milliliters of our NaOH. And that's important for us to know, but we can measure that in the laboratory. We actually put it in there, so that's okay. And then what we're going to do to this is we are going to then use the burette to add this in a stepwise fashion, right? And so we kind of add this slowly, and we add it slowly, we add it slowly, we add it slowly. And what's going to happen is the reaction is going to happen. And pretty soon we're going to get to the point where all the NaOH that's in here gets used up. And we call that the end point of the titration. Now, when all the NaOH gets used up, when we hit the end point of the titration, we have to have a way to detect it. And so what is going to happen, and what we're going to see in the video, is we in here can put what we call an indicator in there that will tell us when all the NaOH gets used up, when it becomes the limiting reactant. And so that indicator is great because what we'll see with that indicator is that indicator will change color, and the solution will change color. When we add a single drop down here, it will go from being clear to being pink. And when we see that pink, that tells us that all the NaOH has been used up, our limiting reactant is gone, and we need to stop adding, because we can continue to add all we want to, but we want to get the best titration is when we see that color change with that single drop. Okay, and then what we can do is we say, oh, well, we added, 50.0 milliliters of NaOH to get to that single drop color change. And so we can measure how much we add. Then if we look here, then it just turns into a stoichiometry problem. We can figure out the moles, right, that we add there. Oh, whoops, got a little happy, right? Moles that we can add. We can use our mole ratio to get the moles of the NaOH, and then we can use the volume that we measured out to figure out what the concentration will be. So let's look at the video, and the video is going to show us what that titration is going to look like, and then we will look at a problem to kind of solve it, right? And so let's look at this video here, okay? And so again, what we're going to see in the video, once it pops up, should have queued it up beforehand, okay, is here, let's say, is our NaOH that's spinning, right? Here we're adding some of the HCl, right? And we saw it start to turn pink, but it doesn't stay pink. We wanted to add it until it stays pink. And so now what you're going to see is they're going to start adding drop by drop, and we finally get that pink color. And once we hit that pink color, we are at the end point of the titration, and we're not going to add any more. Okay? And so that's how that works. Now, so if we were in the lab, that's what we would do. And we're going to kind of get a simulated lab with this either tomorrow or Monday. So let's see how that works, all right? And so let's say that we have this problem, and vinegar is an aqueous solution that contains acetic acid. And we put 10 milliliters of the vinegar into our Erlenmeyer flask. And when we did that, and we put some KOH that had this concentration up in our burette. Okay, so if we kind of think about what we were just doing there, well, if I could draw, right, and then my burette is here. And so here I had my 10.00 milliliters of my acetic acid. Here I had my KOH, and this KOH had 0.2560 molar. And I don't know what the molarity of this is. That's the problem. So what I do know, though, is these two things will react in a double replacement reaction. So I have C2H3O2 plus KOH, right? And then I know that that's going to give me my KC2H3O2, my potassium acetate, plus my H2O. So there's my balanced equation, okay? And so now, if I'm looking at this, right, there's this stuff in there. I start to add this down, and so I add and I add and I add, and then before too long, I see that lovely pink color here that stays permanent. And that pink color kind of stays permanent after I added 31.45 milliliters of my KOH. So the question is, okay, now how do we do this, and how do we use this to get that? Well, we're just going to do our stoichiometry. So now I know that I added 0.03145 liters of my KOH, and I know that I had 0.2560 moles for every 1 liter, because that's the molarity, which means I added 0.00805 moles of KOH. Now, Then I know 0.00805 moles of KOH, and my mole ratio is 1:1, which means I have 0.00805 moles of my acetic acid. So in my Erlenmeyer flask, to start off with, when I put my 10 milliliters in, that 10 milliliters contain my 0.00805 moles of my acetic acid. Now again, I'm looking for my molarity, which we know is moles of solute over liters of solution. And so here I have 0.00805 moles of my solute. Now my liters of solution is 0.01 liter, and that's going to give me my 0.805 molar acetic acid solution. So I was able to use the titration to figure out what that concentration would be. Okay, so hopefully that makes sense. You gotta work on those practice problems that you have in the book. Reach out if you have any questions about this. Let me know if you have any problems. All right, guys. Peace, love, happiness, and thanks for playing.